All right, we are at section 15.2, Coulombs Law, and we're going to use this quite a bit in this chapter. It's properties of electric force. So the electric force is directed along a line joining the two particles and inversely proportional to the square of the separation distance. It's proportional to the product of the magnitudes of the charges of the two particles. And it's attractive if the charges are of opposite sign and repulsive if the charges have the same sign. So here is the equation. Force equals KE times Q1, Q2 over R squared, where KE is the Coulomb constant. And we'll give that to you in a minute. Q1 is the charge of the first particle. Q2 is the charge of the second particle. Notice that they have absolute value signs, so at this point it doesn't really matter whether it's positive or negative. We figure out the direction of the force based on the charges. And the R is the separation distance, so it's a 1 over R squared law. So as you separate the two particles, the force drops off as 1 over R squared. And KE, the Coulomb constant, is given as 8.9875 times 10 to the 9th Newton meter squared per Coulomb squared. So if this separation distance is in meters and you square it, and these are both coulombs, this is going to be Coulomb squared. So you'll see that the meter squared will cancel this, and the Coulomb squared will cancel this, and you're ending up with newtons, which is the force we want a force, and we want it expressed in newtons. So that's going to give it to us. Let's see if I missed anything. All right. So here is a table of the different particles that you find in an atom. The electron, the proton, and the neutron. In the first column, numerical column, is the charge. So you can see that the electron has a charge of minus 1.6 times 10 to the minus 19 coulombs. A proton has plus a positive 1.6 times 10 to the minus 19 coulombs. A neutron has no charge, it's neutral. And then the masses, you can see that the mass of the proton and neutron are very close together, 1.67 times 10 to the minus 17. I'm sorry, times 10 to the minus 27. And the neutron is very nearly the same, 1.67 times 10 to the minus 27. If you were to carry out the digits, you would see that the neutron is slightly larger than the proton. And now if we were to deal in 1 Coulomb charges, it would take 6.3 times 10 to the 18 protons to equal 1 Coulomb. So 1 Coulomb is a very large number. We normally deal, I think I said it in the past, in microcoulombs or nanocoulombs. Those will be the values that we use. And okay, so here's two like charges, both positive, and they repel each other. And this goes along with Newton's third law whether you have a force, you have an opposite and equal force. So there's a force of 1, 2 in this direction and the force of 1, 2 in that direction. If they would both be negative, you would see that it would look the same, only these would be negative blue balls, okay? And charges with opposite signs attract each other. Here you have a plus and a minus, and you have the F21 going in that direction. You have an equal attractive force going in the opposite direction, F12. Okay, so notice how it looks very similar to the gravitational law. The Coulomb's force looks like the gravitational force, where the KE is equal is replaced by the G, and the Q1, Q2 are replaced by the masses, and the R squared is the same as the separation distance. We'll see that electric forces are attractive or repulsive. Gravitational force is always attractive, and the electric force is much stronger than the gravitational force. So the electrostatic force, or the electric force, is much, much stronger than the gravitational force. And electric fields is the next section, and we're going to stop this share and play a little bit with this screen that we're going to play with a lot. Let's see, where did I lost it? Where is, there it is, it's way down there, Google Chrome. Now this is a simulation website, fet.colorado.edu. I think we did it with one of the other, I think we did it with a simple harmonic motion experiment. In fact, the experiment that we're going to do with electric fields is going to use this this site. So I'm just going to show it to you. I'm just going to put a positive charge there, and oh look, these are the field lines. We're going to get to electric field in a little bit, but you can see. Let's just put another particle here. Oh, it doesn't show the repulsive. Let's take this down, put it over here. Let's take this test charge, which I know is positive, and let's look at the force. Okay, this is positive, this is positive. Which way is the force? It's in the opposite. It's in the opposite direction. It's facing away from the proton. And as I get closer, as I minimize R, look what happens to the force. And if I take it away, look what happens. It diminishes. So it grows when R becomes small, and it diminishes as R grows bigger. Now let's switch these and go with a negative charge of -1 Newton per Coulomb. Let's get rid of those electric field lines, and let's just play with the sensor. And there's the force. It's towards the negative, and there would be an equal and opposite force in this direction. You can see as we get closer how big it gets, and as we move away, it diminishes. So bigger as we get closer, and it diminishes as we get further away. Okay, so we're going to be playing with this. We'll play with it a little bit more in the next section on electric field lines. That is the next one, section 15.3. So I just wanted to introduce you to this. We're going to be playing with it, and we're going to be doing an experiment with it. Okay, let's end this.